again, hello. I'm Dana Zhang, and I'm currently an associate professor of the practice at Vanderbilt University within the computer science department, also at the Data Science Institute. I also wear multiple hats besides my full-time teaching gig. I also am the director of graduate studies for the online master's program in computer science. That's part of School of Engineering. I'm also one of 4 or 5 core faculty member for the initiative on the future of learning and generative AI. So you can kind of see where my expertise has been kind of directed to in based on these different roles that I've been. I've been very fortunate to be with both Belmont and Vanderbilt. They have really, these places and programs have definitely trained me to become a much more effective teacher, and also just to, help me also grow professionally as a computer scientist. So Belmont actually contributed to most of the courses that I've taught in the past. Overall, I think I've taught 20 different courses, starting from the very beginning level introductory to Python or data science courses to more advanced ones like big data scaling or machine learning and deep learning. So if you're interested in talking more about those sorts of things with regarding to computer science topics or data science, I'm happy to chat with you further afterwards. Okay, so the agenda for today is quite short, but we do have a lot of content to cover. So I wanted to kind of motivate the talk by giving you some challenges that are currently facing the world of data science, which will hopefully lead to some natural intuition for why we need things like MapReduce and Spark. Otherwise, my talk would be very boring. So here we go. You probably have already seen this graph somewhere in your work, or just from doing a curious search on Google for the demand of large-scale computing around kind of the data volume. So over the last couple of decades, we have definitely seen a tremendous exponential growth in terms of the data volumes that people are generating and we're collecting. So the motivation here is, well, given this increasing in data demand, can we really pair this with the commodity hardware that we currently have accessible really easily to us? So commodity hardware is usually things that are you can purchase, like servers or computers. Think computational engines that you purchase from places like Best Buy or other more serious places where you can purchase additional computing resources. These are usually cheaper, but a lot more accessible to people with a certain number of funds or a certain number of opportunities to purchase these equipment. So it's probably not the greatest idea to run a lot of your data on only commodity hardware. And so here's the motivation. Imagine that you are working either in healthcare or in finance or in any other industry that's generating easily over 2 petabytes of data. So in case that's not super clear to you, I put that into terabytes. So that's equivalent to 2,000 terabytes of data. So this is a humongous volume of data set. Imagine you're scanning all of this data so that you can get some insight into what the data is telling you. Imagine that you also purchased one machine from Best Buy and you have this one node that you're currently running locally. You plug it into your wall and it's working, and you are trying to scan all of this data in this one node of machine. It's going to, let's say, it's pretty good. It's actually able to process 50 megabytes per second of your data. And this is actually going to take you about 1.3 years to actually finish processing. So it would be nice for us to have some really powerful, parallelizable computation resources. So hopefully we can kind of reduce this time. And it turns out that we already have these things available. So let's say we have a cluster of machines that we can either purchase or try to rent from these enterprise systems where we can potentially get 10,000 nodes in a cluster, and that's going to actually shorten the time drastically to only 67 minutes. Right? That's a huge reduction in time. And the other type of demand comes from kind of that need for a common infrastructure. So yes, we have access now to all these really powerful and distributed engines, hardware. How do we actually work around these different types of hardware? Because there's probably some servers that are running one Linux distribution that's in Ubuntu. Another one might be running a CentOS, and some other things might be running Debian. How do these different things communicate with your data needs, your data analysis tasks? So you kind of need a common infrastructure to be able to speak to all of these different types of hardware with their operating systems and their instruction architecture sets. So we need something that's super efficient, reliable, and also easy to use. That's kind of the motivation there. And hopefully we can have something that's open source. So again, very easily accessible for people who are trying this out for the first time. Maybe they're not really ready to invest in Google Cloud Service, purchasing credits, unlimited on end. So before they decide to invest in this fully, they can hopefully try this using an open source version of the system. So Apache license or any kind of open source license would actually be ideal. Of course, these things don't come for free. There are usually a lot of challenges when it comes to working with these highly distributed and large cluster of nodes. One of the major challenges with data is that data, as you can see, it's 2 terabytes or 2 petabytes. It actually has a lot of gravity. So physically speaking, right, it actually is going to weigh your computer down in the sense that it's going to take on a lot of your memory. It's going to take on a lot of your network bandwidth if you're trying to ship that data over to some other computational resource. So this is going to take time. And also the other challenge is these commodity hardware devices like your nodes or your servers, like imagine your computer's not failing. That's just not possible. I think when we have a computer, no matter what version we have, it's going to die on us at least once a year. Ideally, hopefully, it's not going to happen to you this year, but just expect that commodity hardware to be failing on a daily and very regular basis. So in this situation, we're saying that failure is actually expected rather than the exception because it just happens all the time. So how do we deal with this type of challenge? And also the number of nodes in a cluster, therefore, is not going to be constant, right? Even though we have a 10,000 node cluster, because of all these constant failures, sometimes we may only end up with 5,000. Realistically speaking, that doesn't really happen, thankfully. But sometimes you could end up with 5,000 nodes or 9,000 nodes. You just can't really guarantee how many nodes you're going to have within that cluster. So how do you deal with the dynamic changes and constant failing machines? And then the last challenge here is how do we really distribute the computation? So we want to have a way to not move the data so much. So maybe the model needs to become, let's go ahead and move the computation a little closer to the data, but how do we actually distribute the computation? And how do we actually make it easy to write distributed programs so that we can fit the needs for our programming users, so they don't have to worry about configuring all of these different operating systems, installing tools and other things that they need for doing really the data science work on those, right? That's going to be a lot of headache and overhead for doing all of these things if they have to manage it for every single node that they have in the cluster. Again, just to mind you, we're looking at like 10,000 node cluster here in this example. So hopefully I'm getting you excited and curious about the major topics for today, the Spark and the Hadoop MapReduce frameworks. So the ideas here, main ideas are, let's just go ahead and bring the computation over to data so we don't have to move the very expensive, very heavy, gravity-weighted data over to the computation engine like we used to do. And we also want to replicate our data for reliability. We have a lot of data. And when we are trying to store a single copy of that data, that's really critical, mission critical, right? It's worth a lot of, it's actually taken from a lot of people's time and resources to collect all the data. What happens if our machine fails? Because we all know that now it fails all the time. What happens if our machine fails? Well, does that mean we lose all of our 2 petabytes of data? We don't want that to happen. So the idea is let's go ahead and replicate that for reliability. So here comes the solution. We're going to have to introduce a new programming model for doing this parallel computing. And here's where I will introduce Hadoop, MapReduce, and Apache Spark to you guys as the new technologies that can help us solve these challenges and hopefully make things a little bit easier for the modern data science work. And okay, so now that we have this computational model, but we still have to take care of the other challenge, which has to do with the storage, right? What do we do with the data? We still have to kind of figure out a way to replicate it. So this is where you can leverage things like your distributed file system. So Google has their own version of file systems. Hadoop also has their version of distributed file systems for replicating the data files. And feel free to interrupt me at any time if you guys have any questions or comments. So just to give you a quick rundown of what a distributed file system looks like and exactly how it replicates. So let's say that we have 3 different files. Again, these are really, really big files. So each might be 1 terabyte or petabyte of data. So very, again, very heavy and very large. It's going to be very hard to move all of these things across the network, within some reasonable amount of time. So the idea of a distributed file systems is you have each file being splitted into multiple chunks, and you store only a portion of those chunks into one particular, one or a selection of servers. So like in this example, the file in green, that's file 1. Now it's being splitted into 3 chunks, and we're storing the first 2 chunks, chunk 1 and chunk 2, in the chunk server number 1. We're then also storing the other 2 chunks, so chunk 1 and also chunk 3, into the second server. So now you can kind of see the way that the files are being replicated is really helping with our replication, because it's actually being distributed and also replicated across different servers. We do the same for the second file. We do the same also for the third file. So the benefit of this is, now let's say if my chunk server 1 goes down, again, this happens all the time. So my machine just dies. And what happens if I want to retrieve the file 1? Now, hopefully you can see, okay, well, I have the other chunks available elsewhere. So even if when chunk server 1 dies, I can still go to chunk server 2 to get the first part and the third part. And then I can go to chunk server number 3 to get the second part, right? I could do this without having to rely on that first one that died. So that's kind of like a really nice way to support fault tolerance. And in addition, now you can probably think, well, since all these different parts are being stored across these different nodes, probably we could start to pull data from each one of those servers in parallel. We don't have to actually wait for one machine to finish processing before we take out the next part. We can actually do all of this in parallel. Right? So that's kind of the reason why having a distributed file system as the backend is really important and critical to support all these distributed processing and parallel computing in the big data world. Okay, so the early model that uses such a distributed file system, of course, that's your MapReduce. And this is really just a style of programming designed for very easy parallel programming, and it makes the management of your hardware and software failures almost invisible. So again, the programmers, remember that we want to make sure we're trying to protect our programmers. So instead of having to write code and then do a lot of DevOps work, they can only focus on the task that really is critical for them. So this is where we're going to abstract away all of the hardware configurations and figuring out how do we manage situations when software fails. We're trying to take that away from them. So MapReduce can do a pretty good job with that, and I'll explain shortly how it's done. And also it has pretty easy management of these very large scale data because of replication. So it will, by default, out of the box, immediately help you with the distribution of your files. So you don't have to figure out how do I chunk the file into like 3 or 4 chunks. It will actually know how to do that for you. And it actually has several implementations. So MapReduce itself has the open source version in Hadoop. Also, Spark implements MapReduce as well. It's also actually compatible, but it does a lot more than just doing the MapReduce, which again, I'll talk about shortly. And the original Google implementation was just called MapReduce, so that name kind of got stuck with the rest of us. And the idea of MapReduce really came from functional programming. And if you haven't used functional programming, there's the concept of higher order functions. Essentially, this is just any function that can accept another function as inputs. For a basic function, we all hopefully have written functions enough to know that a typical function just takes inputs and produces some outputs right after it does the processing. But a higher order function actually takes in a function as input. So that's kind of a cool way to think about how this function can manage all the other functions and kind of can apply these other functions to some other different situations. So the map part is really just, okay, given this function that I have, let's go ahead and apply this to all of my input data. And the reduce part is kind of like the name suggests, it actually aggregates combines, reduces all of your data. So your data is now going to be a little bit more condensed. And in usually data science practices, we have a ton of data available. Of course, we don't want to give all of this data to our clients. We want to have some kind of a condensed insights or portfolio over to our client. So this is where you need a lot of reductions, right? You need a lot of the compression. Okay, so here's a quick diagram to kind of show you the architecture of the MapReduce. I feel like the phrase MapReduce doesn't really give credit to this really important phase called shuffling. So this is what I was trying to do in class 2 and also today, just to make sure MapReduce is also giving shuffle, the important phase, some credit. So it's actually going to be the map and then shuffle and then reduce, and then I'll explain shortly what's happening. So let's say that we have some input data. And by the way, in the Hadoop version of MapReduce, the input data is going to be stored and also grabbed from the Hadoop distributed file systems. For, again, the reason of you have this nice infrastructure like in the file system that's supporting your data needs in place. And the input data is going to be splitted into multiple chunks or partitions inside the file system. And for each split, you are going to run it through some kind of a mapping. So again, think that we're trying to grab, a portion of the file, and we're going to do some processing on each portion. But now that files are distributed across these different nodes, we can actually do them in parallel. We don't have to do them sequentially anymore. And then the shuffle happens to sort your data into usually ascending orders or some kind of an order that you define. And it's going to leverage a lot of the key value pairs to do the shuffling and then figuring out, well, given all these intermediate outputs from the mapper, how do I then send it over for these tasks to be reduced to the reducer? So you have also this part that's doing the merging or the aggregation, and then you send it over to the reduce, and finally the reduce will give you the final output. All right, so if none of that made sense, I have an actual example for you guys. The word count example is kind of like the hello world example in MapReduce, where you have the task as, okay, given a file, a very large file. Usually I have a very small file. In this case, only 3 lines of code or 3 lines of text. But usually, you have a very large file. So again, think like 1 terabyte of data. And your input in this case will be a bunch of words, right? It's just text file. So you're typically, if you're trying to count how many unique words do we have, or how many for each unique word, what is the word count there? So typically in a sequential program, what we would do is, again, load in that entire file, again, 2 petabytes of data into our system. And one by one, we're going to read through the word and process it. Okay, so that's going to take a super long period of time. Again, 2 petabytes. I'm trying to get that number to be stuck in your head so you can see where this is becoming really helpful. All right, so what we do, once again, right, in a sequential world without parallelization, we process 1 word at a time, and then we finally do, okay, well, if we've seen this word, then we increment the count by 1. Otherwise, we skip it and move on to the next word. So the nice thing about MapReduce is now we can partition our file into 3 different parts. So each part is going to take 1 line of text. And so in the first line, in the first mapper, I can actually have the first sentence or the first line of my file as input, so deer, beer, river. And in the second line, I will send it over to another computational mapper. The third line, I will send it to a third mapper for doing the computation. So in the mapping, so this is kind of the splitting phase, getting it all ready for the map phase. So in the mapping process, now what I can do is, okay, for every word that I see, I will quickly give it a count. I will quickly turn it into a key value pair. For the key, I'm going to use the word as the key. So it's going to be a string. And for the value, I will just say, I've seen this word 1 time, so I will put a 1 right there, right? So I'm splitting my sentence into a bunch of key value pairs. And then I do the same, again, like all of these things for each line is simultaneously happening. So all these things are being parallelized. And then I shuffle. So the idea of the shuffle is, okay, you have all these intermediate outputs from the mapper. And if I just do some shuffling and sort everything in the ascending order, given the alphabet order, so we can now have bear appearing first, car appearing next, deer, and then river. And now all I have to do is to kind of, instead of having to do any kind of reduction yet, I'm just going to group by the words, right? Because the words are now all in sequential order. So the bare word will appear next with the bare word. The key value pair will be very adjacent to one another. So it makes it easy to kind of do the grouping. So now you can also do some kind of like intermediate reduction here if you want to, but the classic example is you don't do any kind of grouping until you reach the reduce phase. So this is where in the reduce phase, you're going to say, okay, give me each key. I'm going to group everything, or take the group that you have already created for me. I'm going to just basically reduce everything, right? So now it's going to add, okay, you've seen this one time, another mapper has seen it one time. I'm going to go ahead and add these two values together. So for the bare example, it has seen this twice, so it adds it to condense it to 2. For car, it has seen it 3 times, so it's going to add it to a total of 3. Right, so I have now finally a key value pair for each word and the count for each unique word. And then finally, I can output the result. Right, so this is a pretty cool process that's happening, because again, I'm able to splits my inputs into multiple chunks, so I can do a lot of parallel computing at the same time. I don't have to rely on the first line to be done now. I don't even have to rely on the last line to be done next. It's in whatever order that the nodes are happening. Okay. Is this making sense? Yes.
Why do we need to do shuffling? Why do we need to run the reducing directly from that?
Yeah, so that's a good question. So the question is, why do we need the shuffling phase? So the shuffling phase, the name of shuffling kind of is a little misleading. Shuffling happens to actually allow you to sort your elements by key. So you're not only just shuffling, you're still shuffling, but there's a purpose. So you're trying to sort all of your key value pairs by the key. Yeah, so that's how you can later group the adjacent ones together, and then finally you can have a nicely reduced pairs of key and value. Okay, so the Hadoop distributed file systems architecture is kind of shown here very briefly. Typically, you have some clients interested in doing some kind of data processing. Remember the idea of bringing in your computation over closer to your data. So the client will actually write some code, and that code is actually going to happen inside your Hadoop file system. So again, this is the idea of me trying to, we trying to bring in all of this computation closer to the data. So imagine a client is trying to do some processing on a particular data file, so it brings in that processing over to the data node. So the data nodes are basically things that are managing all of your files, the different partitions of the files for you. You also have a name node that's managing all of the metadata. So it knows, this is kind of like the nice manager there. You don't have to worry about how your files are split. The name node actually has all that information. So if you need a file, let's say number 5, it will know, okay, well, in my table of directory, or in my file directory, or in my table of contents, I will be able to find all the chunks that are part of your file number 5, and I will go grab the pieces for you, or I will tell you where they are, so you can go send your program over to those data nodes. So that's kind of the idea. Okay, so I wanted to show you some code, hopefully to make things a little clearer. This is a mapper program that I had asked my students to write, so that they can kind of get used to the Hadoop ecosystem. Typically, you can see this is fairly straightforward, but still it involves a lot of Python coding. You have to make sure you're reading in from standard input your lines, so your text file. And you're going to then do some tokenization, so doing some pre-processing, so your words are all, let's say, lowercase. So otherwise, it's going to treat the uppercase the uppercase T as a different word compared to the lowercase stuff. So it's going to tokenize your words first, converting everything to lowercase, and then it's going to emit the word. So this is where it's creating the key value pair. And by default, Hadoop uses a tap character, so that's why you see the \T. So it uses that to separate your key from the value. So you have your word first, and then that one count. Right? So we're just basically saying the mapper has seen that word, so we're going to set it to 1. And then you have to program a reducer which is going to help you do the consolidation. So you're going to consolidate all of your values for you, that as long as they're the same key. And if you look a little closer at what's happening, is we're still processing every, so the reducer, of course, will take on as inputs the outputs from the mapper, right? So these are kind of the different phases that we go through. So the reducer will take on the map output, again, which are just a bunch of key value pairs, but they're sorted in that decent or alphabetic order. So then we can take our every single line in the intermediate outputs from the mapper and split it into the key value. And then because we're doing things sequentially, right? So if we have seen the same word, so that means, okay, we're still looking at the current word, so let's go ahead and increment the count or add the previous count there. Otherwise, if this is a new word, we can move on and restart our word counting process. So that's the benefit of having that sort. If you don't do sort, then this is basically not happening for you. Right? You can't rely on the for loop to kind of process these things sequentially for you. Okay, and then you haven't finished your task yet. You just finished implementing your mapper and your reducer scripts. Now what's happening is you have to actually submit all of your mapper and reducer as part of your MapReduce job. So MapReduce is pretty cool as a model to help with parallel computing, but that's one of the reasons why I called it kind of like an earlier model, because it's a little bit clunky, because you kind of have to do a lot of programming in Python, and then you have to use this random, but again, very useful command line option to pass in all of your mapper, your reducer, your input file, your where you want your output to be, and then you have to specify some environments for your current file, and you run this. So this is the API from Hadoop streaming, which is supportive for Python. So in the underlying Hadoop ecosystem, it's actually being implemented in Java, and a lot of data scientists don't really write Java programs. So that's why we leverage the Hadoop streaming API to help us write Python code. So we do this, and finally, hopefully we can get our output. Okay, so usually this will take a really long time because, again, it's grabbing the file from Hadoop file systems and then doing the processing, and then finally the output will be put back into the Hadoop file system. Right. So are there limitations? It's a cool model, but of course there are always limitations. So nothing is perfect. There's always limitations to a previously existing paradigm. So the challenge here is that your Hadoop version and other versions of MapReduce will actually heavily rely on reading and writing files to and from a distributed file system. And we all can see now that these distributed file systems are pretty clunky, right? Because it's supposed to support a lot of replication. So it's going to be a little slower. It's also storage. It's also made up of a bunch of commodity hardware. It's basically stacking a lot of those servers together. That's why you see in data center pictures, you have racks and racks of machines. Yeah, so that's that. You've got it. You've got your commodity hardware just sitting on top of each other. So it's very slow to kind of start up, but once you have it, it can get going. But there's that setup speed or the startup time. So what's the problem with our data science? Well, it turns out a lot of your operations are actually carried out on the same data set. So each time when you run MapReduce, you actually have to load the data back into your environment, and then you can run your mapper and reducer, and then you put the output, you dump the output back into your file. But what happens if you're trying to run multiple machine learning models on the same data set? Well, for Hadoop, MapReduce, unfortunately, you have to load it every time when you have a new training model available. So that means for each new model you have, you're going to have to do a data load, which means, again, starting up the machine, the commodity hardware that's kind of cheap and slow, and things will probably crash, and it's just not very efficient for doing data science work. And it also doesn't have the support for interactivity. So hopefully you saw that with the 2 Python scripts and your Hadoop command, that's all you've got. That's all you have to do. You program in Python and then you write the command. There's nothing else that you can do to kind of debug your code. So that's where that's the lack there. So if you don't have REPL, so REPL is the read, evaluate, print loop, right? If you don't have that support, then, well, guess what the problem is for data science? It means you can't test out your code, or you can't run ad hoc tests. So that means you can't really validate your intermediate results, right? What if your analysis is wrong? Then, well, if you don't catch it, you're going to have to wait until all of your analyses are done to realize, oh, I made a mistake somewhere in the middle. So now, that's kind of painful. We don't want that to happen. Yeah, I'm already getting you kind of like thinking about the problems with MapReduce. So in addition to these first two limitations, the last one is like for these complex jobs in MapReduce, well, we can't really support them very easily. So with MapReduce, again, the idea is that you figure out some ways to parallelize your tasks for each partition of your inputs, and then you figure out a way to kind of reduce them. But in the real world, a lot of jobs or complex tasks aren't just as easily doable as the word count. So certain situations, you can't easily find a mapper or reducer for your tasks. So again, the problem for data science is really not specialized for machine learning, right? Can't really easily parallelize them. Okay, I think this is just a repeat. All right, so this is where I'll introduce another solution called Spark, Apache Spark. And this is written in Scala and originally developed at UC Berkeley from a really highly distributed cloud computing lab. And it's supposed to be a very fast and expressive cluster computing system. So again, it already out of the box, it provides you with the way of working in a large cluster. And it's designed to be fault tolerant, so it will preserve a lot of the properties that you get from your Hadoop distributed file systems. So it will help you replicate your code, replicate your files, so you don't lose any data in any way. And it's also going to have a lot of these optimized support for doing very general execution or computational graphs. The key, I guess, at the core of Spark, the data structure that's the most important, that contributes to Spark's advantages and all these really nice properties, is really called an RDD, which is a resilient distributed data set. So it's supposed to be resilient and also distributed, right? And it's also compatible with Apache Hadoop. Okay, so here are some of the adds to in Spark that extends beyond the MapReduce model. So it's actually able to cache your data for competitive, repetitive queries. And if you are able to cache things, so when we talk about caching, we are actually looking at storing data in very fast memory. So that's why usually when you buy a computer, you can have 1 terabyte of storage, but you can't have easily 1 terabyte of RAM. Right, that would cost you a crap ton of money. Usually, we don't buy computers. It's also not really, commercially available, unless I guess you're these manufacturers or high tech companies. So we don't really have a lot of very, very easy access to these cache, again, very fast memory. But thanks Spark for coming up with this model so we can leverage kind of the nice collective cache for using or using in our data science process for doing a lot of these computation. So supposedly it's about 100 times faster than Hadoop. Again, you're putting all of your things into really fast memory versus very cheap commodity hardware. So hardware disk storage. And you're also, so another cool thing about Spark is trying to save all your intermediate results instead of to disk, it's trying to save it to cache or the fast memory. Okay, and it also provides a lot of the functions that are actually designed for data science and graph processing. And in addition to database management, also it has a lot more APIs that it can support. So for Java and R and Python programmers and even Scala programmers, it's actually available very easily. Yes.
Maybe ask a silly question. So you mean the cache means all the data in your graph?
Right. So cache usually means, yeah, like RAM, that's usually very fast or expensive memory.
That means it's also loading all the files to graph.
That's the idea. Yes. So the question is, so when I talk about like RAM and cache, that's basically really fast memory. And Spark will have instead of loading all of your files into this collective, very expensive fast memory all at once, we will have to do some kind of an optimization process to make sure we don't overextend our memory. We don't basically use up all of our fast memory. So here's a quick look at the stack for Spark. You can see right out of the box, it supports like SQL in Spark. It also supports streaming, which is basically taking input and shoveling it and producing an output.
Again, apologies if this is a basic question, but I think I get the idea of how you want to, how you want to run frequent queries in cache, but you maybe give an example of what would a more of a problem with, we've got these very frequent queries and a whole bunch of less frequent queries. I'm assuming this allows to be where 20% of your queries are keeping up 10% of your computation. But is there a good example of that? I think I get it, but I'm not sure.
Yeah, so typically when we are, again, like looking at large data sets, we can usually divide the data sets into multiple portions. And then the idea is that we can like parallelize the tasks, right? And then the idea is that through some kind of, I'll talk about transformations later, but you can transform your data to become much, much smaller in size, right? So then we rely on Spark to figure out, okay, given this reduced version of the data, can this fit in memory? Can this fit in this really fast cache that you have?
Okay.
And usually when we are looking at Spark, again, this is designed for doing cluster computing, which means it will have, memory, again, like cache memory or very fast memory that's a lot larger than what we can purchase from any, single store. So usually collectively, this is pretty large. And the idea is that it should handle at least, 10 gigabytes of data without any problems. Yeah. And you can see it's also compatible. So Spark is also compatible with other types of data structures and also resource managers like Cassandra, that's a NoSQL database. You have Mesos, that's another resource manager. Okay, so Spark compared to MapReduce, again, where all of your inputs are coming from Hadoop, the distributed file systems, and you're dumping all of your outputs to Hadoop. So you have two ends. On each end, you have to do some very clunky file operations, right? So in comparison, Spark will do processing in memory. It also is going to be able to collect data from multiple sources. So let's say I have a file that's currently sitting in AWS S3 storage. So that's kind of like a storage bucket that you have available through Amazon Web Services. You can actually take that data and feed it into Spark. So again, you don't have to put that data ever into a distributed file system, right? You can just grab it from any source. Of course, it's compatible with Hadoop file systems, but you don't have to have it in there. And then it's going to basically process all of your inputs inside RDD. So it's going to try to create these, again, very, very resilient and fault tolerant and distributed data sets for you. And then you can also partition these and then or distribute them to different output sources. So you can dump them back into a Hadoop file system or go ahead and store it back into S3 or somewhere else. So it's very heterogeneous when it comes to the sources of data, input and also output. All right, so a little bit more on RDD. So again, this is kind of like the primary player or the core component to Spark. And essentially, it's a collection of elements that you partition across all of the nodes in your cluster. You can also operate on them in parallel. And once again, this is just showing you that RDDs can be created from all these different sources. It's not limited to any particular type. You can submit JSON files, text files, or you can also create RDDs from other RDDs or other ad hoc data types. And the key thing here is that Spark's RDDs are designed to be immutable or read-only. So you write once and then you create it, but it's going to be partitioned and it's going to be a collection of records. So the important part about this being read-only or immutable is imagine that you're trying to run one type of operation on this RDD that you think you're going to process later, right? So now that so you're currently doing, let's say, task A on this current RDD, and then later you do some other tasks on the side, and then finally you come back and say, okay, given this original RDD, now I want to compute task 5 on this. Okay, so like 4 time steps have passed. So if the RDD is not immutable, your original RDD is not going to be original anymore, right? So it's probably, there might be some kind of I guess a tempering going on with your original RDD. So it kind of destroys the data integrity in a way. So that's why it has to be immutable, and it's designed that way. And RDDs can automatically recover from node failure. So again, Spark creates and provides all these managers to constantly be checking for node failure. So it kind of manages all of those on the back end for you. And you can also track the history of the partition. You can also rerun your RDD or recreate your RDDs using what's known as like a lineage of the history of your RDD. So it will help you kind of store the evolution of your RDD. So where did it come from? What operations were performed on it? So you can always kind of recreate the original.
So you have like an immutable record, but you are able to manipulate that record to end up with a new record, I guess. Right?
Yeah. Yes.
Okay. So we'll just say there's different file versions, but each one will have like
each one will have a different name. Exactly. Yeah. So every time when you perform any kind of action on an RDD, it's going to create a brand new one for you. They're just different. Yeah.
So like a practical example, like if you're trying to aggregate revenue by month, and then later on you want to aggregate revenue by month by sales rep at the same time, that would essentially create two different RDDs.
Exactly. Yeah. Good question. Yeah.
What's the difference between RDD
and RDD is a special data set that is designed to be distributed for the Spark system and also for distributed file systems. So it's just kind of like a very Spark specialized data set or a data structure. It's more like a data structure. It varies. You can store very small RDDs. You can also store very large RDDs. It varies as long as it fits in memory. These are good questions. For the Spark architecture, you can see it's a little bit more simplified. So typically you start with a driver program. So this is where you start a Spark context. So you can say, okay, I want to go ahead and create a Spark environment. I want to start working with and playing with it. And it will start to communicate with the cluster manager on your behalf. And then it's going to start sending some of the physical or actual tasks to these worker nodes. So again, this is where the parallel computing happens. You have multiple worker nodes doing very similar tasks, but on different portions of your RDDs. All right, so there are, probably this will also help you guys understand a little bit better and appreciate what is really the key advantage of Spark. So there are two types of operations on a Spark RDD. So the first one is called transformation. It's really a fancy word to say, just whatever you do on the data, you're changing the data, that's your transformation. Right, so you could go from, I'm going to do some filtering, I'm going to do some mapping, I'm going to do some grouping by, or I'm going to reduce it by key. These are all operations, or all transformations, because your intention is to transform your data to form a different version of this earlier data. So each time when you make a transformation, so Spark will remember that transformation for you. Okay, but there is a point about lazy evaluation. So the idea is that the transformations actually don't produce any data. They just produce RDDs. So RDDs, you can think of this in this context as I have some metadata about where each new RDD came from. So maybe this current version came from the raw file. And now I am going to perform let's say a map operation on it, right? So it's going to remember, okay, it came from the original file, and now I'm going to apply a map on it, and then I will keep on going to create the rest of the newly transformed RDDs. So these are just, again, like a bunch of metadata. Until an action is called, so there's nothing that's happening. There's nothing that's materialized in the data. So you don't actually have data being stored in an RDD. It's just a bunch of meta information. Right? Think of it as like a framework for how to come up with a new RDD or your game plan. And so when an action is called, this is where you can start having fruitful results from your RDD. So this is basically where your data gets materialized. So all the transformations that you have done in the past now is going to be collected, and finally you can start to see final results or final product from your action and transformation. So things like count, right? So I count, okay, how many records are currently in this RDD? That's an action because I'm getting data back out. I'm getting some like insight back out from the data. Collect is basically a method that gets you to display or to give you all of the values back. Take is you can take however many you want. So you can specify a number. You can take 5, so it's going to produce 5 records. You can take 1, it's going to give you 1 record back. All right, so here's some code. Same exact word count example implemented in Spark instead of MapReduce. So I created a very small file so we can kind of understand where this is going. So this is just a very small test file. You know, you have some uppercase letters, some a lot of lowercase letters. So this is the same exact split into words function that I had in my mapper. So I'm basically trying to take all of my letters and convert all of them into lowercase letters. So my spelling, my letter case is consistent, right? So that's all I'm doing here. And I printed out the output just to show you, okay, it's actually going to do two things. It's going to go ahead and first of all, convert all of your letters into lowercase letters, and then it's going to split the single string into a list of strings. Right, so it splits each word out given the white space. Here's one way of how I can create an RDD. So this is a Spark context that I've set up. So I'm connected to a Spark computing cluster. So I'm actually in business. This is my driver program. So I can parallelize this data. So now Spark knows, okay, well, maybe I need to put this into 2 partitions or 3 partitions. In this case, probably 1 partition. I don't have a ton of data. So probably all fitting in that one RDD, which is going to be called simpler RDD. So again, this RDD doesn't actually have file. If you try to do a printout of the simpler RDD, you don't have any data that's listed here. You only have, okay, it came from a file, and okay, it's being parallelized, right? So there's no data. The data is not materialized yet. Okay, and then we can of course do some transformation. So flat map is going to allow you to take a single value, a singular value, and convert it into a list of values. So I started with a single string. Now I want to run a flat map so I can get a list of words. So this is what I do. And I pass in the split into words to tell flat map how do I do the transformation. Again, this is all still being lazily evaluated, meaning that there's nothing that's happening. I'm just trying to give you kind of the recipe for how to perform the transformation. And then I will go ahead and map for each word that I've split it out from the previous long string. I'm going to, you probably start to recognize this, where I'm creating key value pair. The key will be the word, the value was to be the one, right? So again, we're trying to replicate that MapReduce example for the word count. Okay, so I have word and then one. And so keys is a kind of like a transformation. It doesn't actually do anything. It will just grab all the keys. And then you call collect. This is where you can actually start to get the data back. So this is once you call an action, all your transformations are going to happen. So when you call an action, in other words, the Spark context will know, okay, it's time for me to send all of your compute to your data nodes, or sorry, your worker nodes. This is when the computation happens. You can do the same for the values. So this is just me trying to show you what are the keys and the values, right? So for the word this, I have one, a count of 1. For is, I have a count of 1. So exactly like what we did in the map.
Okay. So out of curiosity,
yes.
When you run the RDD on it, are you actually running through the transformation twice with that, or is it actually being cached?
Currently, I'm not caching anything.
So it's a manual cache.
So yes, you have to, if you want to store this into the actual fast memory, you have to call .cache here, which is something that you can do to persist your data. So if you want to reuse like simpler word pairs again later, you don't want to have to recompute this RDD, you will have to store it in somewhere that's persistent.
And that may be an implementation details throughout some more than anything.
No, these are, I like questions. Questions make me think harder. And also they keep me awake. Yeah, I used to be a night owl, but I started teaching 8:30 classes. Yeah. So the cool thing here, I guess I haven't really touched too much on the in-memory processing piece, is if you want to go ahead and perform an action on an RDD. Of course, this is when all the transformations are happening. Okay, so finally you get your simpler words, word pairs, all the values being materialized. So again, the data is now being associated with this variable, for example. But until you call collect, there's nothing happening, okay? But if you don't cache it, so that's why I love that question. If you don't cache it, you're not actually leveraging Spark's like in-memory processing, because you didn't actually ask it to, hey, just save this for me, save the results for me, right? I just finished the hard work of processing 2 petabytes of data, and I didn't cache it because I didn't, remember to do this. And it's going to, the next time when you run collect again or run an action again, it's going to recompute it. So it's basically doing that reprocessing the second time around. So that's why it's actually better to have the cache there, so that you can save at least one computation in this example. Essentially, we're calling collect or an action on simpler word pairs twice. Right. So if I cached it here, then I could at least save the one computation. Okay, so then we have to do the reduce. So we just did the map. We mapped each word into a pair of word as the key, one as the value, and now we can reduce it by key. So this is where you can pass in a predicate or a lambda expression where you can say, this is how I want my keys to be reduced. This is the process. If I just add the word count together, then I get the final word count. Right. So in the end, you get the code that's correct. The same exact output or the same exact process, but it's much simpler to do it in Spark, right? Yeah. All right, so I just wanted to touch on this very briefly. Again, you can spend a single semester talking about, or 2, talking about all these like cool things in Spark and all the technical details, but Spark also has the support for a data frame, which is another data structure that builds on top of RDDs. This gives you a higher level abstraction with a structured API, so you don't have to write a bunch of RDD code, right? You don't have to create a bunch of RDDs doing the transformations. You can actually use something that's very similar to Pandas to do all these aggregations for you. So the example here is we can pass in these tuples of values. The first value will be a name of a person. The second value will be kind of like the age of that person. And in this case, we might be curious to come up with the average age of each name that we have in the data set. So like, how popular is Alice and, people who are 20-year-olds. So you kind of get the aggregated insight from there. And then you can just call, okay, let's go ahead and create a Spark session because we're working in Spark. So this is where you it's kind of a little different from Pandas where you actually have to create a driver before you can use it. So you will say, Spark, go ahead and create a data frame for me using the data that I've created in Python. All right, so this is kind of, this part is at least similar to Pandas. And you can pass in kind of the columns or index that you want for your data. Okay, and then you can do group by on it. So hopefully this looks very familiar to those who've used Pandas before, right? Why PySpark or Spark is really designed for machine learning and data science, because it borrows a lot of very cool ideas from Pandas and NumPy. So now you can actually run group by on the name and then do the aggregation on the age column and then also get back your average age. You can also give it an alias called average age. And finally, you'll be able to see a data frame like this, again, which is kind of very cool. But without the data frame API, just imagine how many different RDDs and transformations you would have to create to get here. Right? So that's why, again, like data frames are designed for doing data science tasks. So here are just some of the key takeaways in case, like I bored you to death with all the details. So some of the key things to remember is when you are working with large scale data sets, the processing of those very large data sets actually requires the data to be, or the computation to be moved very close to the data. So in this world, we're doing things in the opposite fashion. So we're, instead of moving data across a very large network of clusters, we're bringing our computation closer to the data. And then for MapReduce, so that's really an earlier and fundamental model for doing programming in a distributed computing environment. So Spark is more of this like modern, a bit, hippier framework for doing more sophisticated tasks like machine learning, training, data processing, whenever you have to work with structured data. So I encourage you to actually check out the documentations for both of these systems for more information. I hope you're curious and we'll continue this journey of learning. And thanks for listening, and I'd be happy to take any questions. don't typically get a round of applause for teaching a class. So thanks for the treat.
So your students that clap for you, they get more extra credit.
you guys gotta meet this guy. He's great. He's great.
Are there questions? We do have time.
I have a question about the parallel processing. Is it only gonna be able to pull from 2 different
Yes,
sections?
that's really cool.
So you can't, we don't have a setup where you can pull from more than 2? Because you cut that data up into 3 sections in the example.
Yeah.
Would be a way to pull all 3 sections at the same time?
It will actually grab it for you. So you don't have to worry about, like, if you want the whole data, of course, like
Right.
you ask Spark to do it for you. So it's going to get you all of the parts that you need.
Okay. So it can pull from multiple, not just 2 throughout basically. When I think parallel
Yeah.
processing, I think there's 2. Like in the first example with the HD,
Mhm. Yeah, I was about to show you kind of that diagram from HDFS.
yeah, HDFS. Okay.
Right here, right?
Uh,
Right here.
No.
No.
Before that one.
This guy.
Yeah, this.
Oh, I remember.
What's the section 1, section 2?
Yes, this guy,
one,
this
chunk one,
guy,
chunk-
this
Yeah, right there.
Yeah.
So you got chunks 1, 2, and 3.
Right.
For file 1.
Right.
So when you're doing parallel processing, you know, say like on chunk server 4, could it actually pull from chunk 1, 2, and 3 all at the same time?
Oh yeah, of course.
Okay.
But then again, we want to rely on the file system manager, like the name node in HDFS, to help us with where we need to grab the data.
Right.
Sometimes like the other
Right.
servers are just a little
I just wonder if
closer.
it could pull from more than 2
Oh yeah.
chunks.
Oh yeah.
Okay.
Oh, definitely.
Okay. So
Like
the
in
more
this
chunks
case-
you cut it into, the faster you can read the data.
Right. Right.
Okay.
So if your compute is actually pretty close to chunk server 4, then you probably can grab all of your data locally.
Right.
Yeah. So you don't need to go to other servers. But the problem is, like, sometimes your partitions might fail, right? A part of your hard drive fails.
Right.
Then you lose access to chunk 1. That's where that replication is helpful, because you can just go to whichever server that has chunk 1 to grab it.
It's kind of like a RAID system, but it's just in service.
Right.
And you just pull the
Right.
plastic.
Yeah.
So what's like the next big thing in big data processing?
In big data processing. I guess like Spark has been the most dominant, or the most like commonly used framework for doing data science work. But of course, there are all these like LLMs these days for supporting, I guess, like more text-based data set. But yeah, Spark is, I guess, the latest that you've got.
This wasn't open source, but I've worked with Oracle's Exadata before. Fun toy, but expensive.
Yeah.
And, you know, a lot of people are moving to Spark and Purdue
Right.
just because of the licensing for that.
Yeah.
But like I said, it was a fun toy.
Like if you use some of the enterprise cloud computing resources like Google Cloud Server Service, or Amazon Web Services, or even Azure, they will have support for Spark. Right, so that kind of tells you, like, if all of these companies are using Spark, then it must be the very popular child of big data.
Yeah, I was curious, like how do the higher level data science tools you mentioned, like SQL, deep learning, how do they interface with Spark? Do they have to be built on top of, does the Spark have to incorporate them like the data frames that we can use them, or is there some way that they interface?
Yeah, so PySpark, we're going to learn this the rest of the semester. So PySpark will have things that are specifically designed, tasks, methods specifically designed for data frames. So you'll see very similar things. Well, actually, I say similar as in like the process will be similar, but we'll see how that plays out for a data frame. Yeah, it's a little bit more complex than what I want to get into today. Yeah.
Well,
Thanks for your
another
question.
question.
Yeah.
So on the last slide, you mentioned it helps the data frame API. When we use the data frame for the Spark, do we need to figure out how we set up the RDD, you know, how many, is it so easy to use, or we still need to figure out, tell the Spark, okay, I have 1 terabyte of RAM. This is the file. I still need to do configuration
Typically, the idea is that the default values or the default configurations will work just fine. But let's say you do have a 20 core machine and you don't want Spark to take up all 20 cores. You want to leave 5 for another process or task. This is where you can kind of go in there and control how many cores Spark will get to use. Yeah, so you can say, okay, you only use a portion of it. Don't touch the rest of the 5.
And that's if it's like some of the other stuff that is out there, like it. There are so many dials and levers and switches. It's a job just unto itself to understand all that and really tweak it. A lot of times, if you really need to just get the most, you need to squeeze as much performance out of it as you can. It's an ongoing process. You'll tweak a little bit.
I guess I didn't show it in this code snippet, but what you could do is when you create a Spark session, for instance, you can actually specify, I want 4 nodes to be created. So it's a very easy configuration from the programmer's perspective. You don't have to go in and do very special hardware programming, if that helps. Yeah, it's very nice. Oh, yeah.
I understand Spark kind of does a lot of optimization for your but is there some things that it can't do? Is that just you as a developer or how to define tool like hey, these instances of transformation, maybe switched around or it's taking longer, more reshuffling happening, and just the kind of partitions that things that you can use quicker and better aided by different, looking at the different data set and doing certain transformations in different order and doing those actions. Difficult, very difficult.
It really depends. For some, for example, like for one machine learning classifier, that's like kind of the naive base model where you calculate a bunch of probabilities. It's very easy to parallelize tasks for that particular machine learning algorithm. But for some that are very dependent on the sequence, you can't easily parallelize this, which means it's probably not a great use case for Spark. So Spark actually does support SQL queries. So the Spark SQL will allow you to actually perform your SQL tasks on your relational data, so your data frame. But it's things that are, I guess, a little bit more dependent on other modules. So when you have a natural dependency, when you can't really parallel, like there's no way you can think of any kind of parallelization, then yeah, we just can't use Spark for it. Right? If things are sequential, like we are always depending on the previous task to be done before the next one, then yeah, you just can't parallelize things like that. Right?
Last chance, questions? Yes, I don't know one. You're also in artificial intelligence. What problems are you most looking forward to using artificial intelligence?
Artificial intelligence. I use. Well, from the from an educator's perspective, I actually really appreciate the the current capabilities in AI to help create all these creative assignment ideas. But in addition to that, I actually currently am working in collaboration with different companies like Bridgestone and AllianceBernstein to come up with ways to use these LLMs to produce more domain specific models to help them with their business. Yeah, so it's like the artificial intelligence or like large language models themselves are starting to reach pretty strong powers, and it's got a lot of capabilities that we didn't used to have at all just a couple of years ago. But now it's a matter of how to use those to inform us about a certain very like niche areas, right? So that's kind of that's where that research gap, I guess, is in industry. How do you actually apply this to a real world problem? Yeah, so solving real world problems, I guess that would be my answer.
Let's give her thanks.
All right, thank you.